let A be an element of H, we've got to look at A inverse. So consider A inverse, which a priori is just an element of big G, but since we know that A inverse is also the inverse of A in H, it must be in H as well. So since A inverse is also the inverse of A in the group H, so we proved that about 5 minutes ago. We know that A inverse is in H. So 3 holes. Okay, so our preliminary remarks have been a help here. So what we've done now is show that if it's a subgroup, then 1, 2 and 3 hold. Well, that's, as I said, that's usually the way around we use the theorem. So we now need to prove that if 1, 2 and 3 hold, then H is a subgroup. Okay. So, conversely, that's a word you often use in the middle of a if and only if proof. We're now going to go it the other way around. Suppose that 1, 2 and 3 hold. I'll just write down what we're going to do. We must show that H is a subgroup. Of G. So remember what 1, 2 and 3 were. 1 was closure under the binary operation. So by 1, H is closed under the binary operation of G. And that was part of the definition of being a subgroup. So what we've got to do now is check that under the induced binary operation, which is guaranteed by 1 holding, that H is a group itself. So that's guaranteed by 1. We need to check that under the induced binary operation, H is a group. Because that's the other bit of the definition of a subgroup. That H is a group itself. So now we have to go right back to our definition of group. So we had curly G1, curly G2 and curly G3. That was Fraley's way of denoting the 3 axioms for a group. We've got to check that they're all true. So associativity is one thing we have to check. That's curly G1. Well, this is something we get for free, because since the binary operation on big G is associative, then certainly the induced binary operation on H is associative. So let's just write that out, although perhaps we don't need to, but let's write it out. So let A, B and C be in H. Then if we do A, B, C, thinking of this as a binary operation applied twice in big H, well, we can also think of this as in big G, and we have associativity in big G. We can immediately write it like this, and then interpret the whole thing as an equation in big H. So that's since we have associativity. On big G, and also using the fact all the way along that the binary operation on big H is just induced from the one on G. So when A, B and C are in big H, then this is also the same as the corresponding thing in big G. So associativity we essentially get for free. If it's true on the big group big G, it's certainly true on big H. So that's associativity. What about identity element? That was curly G2. So what I want to do, remember, is prove that big H has an identity element. Well, let A be an element of H. We know what the identity element's got to be. It's got to be the identity element of big G. It can't be anything else. We've just got to check that that works. So since in big G we have these two things holding. So we started off with little a an element of big H, but it's also an element of big G, and in big G the identity element does this job. But now we can just say, well, since E is an element of big H, that was condition 2. So also by condition 2, which remember we are assuming E is in H. So these two equations and the fact that E is in H mean that E is an identity element for the binary operation on H. So it is easy to get, or slightly easy to get a bit lost in this proof. You've got to keep a clear track of what you're actually assuming and what you're trying to prove. So we're assuming at the moment 1, 2 and 3, and we're trying to show that H is a subgroup. So in this bit, we want to show that assuming 1, 2 and 3, we can get an identity element for H. So we've used 2. The fact that the identity element of G is an element of H, but then the identity element of G certainly does the job of an identity element for H. So H does have an identity element. And then finally, inverse elements. Let A be a element of H. We want to show that A has an inverse in H. Well, we know what that's going to be. Let's just consider the inverse of A in big G. Well, by 3, A inverse is actually in H. So that was the condition 3. It said that for every A in big H, the inverse of A is in big H, and also of course A inverse A is E and A inverse is E. Those are equations in big G, but we can now interpret them as equations in big H because E is in big H. That was condition 2, and so these can be interpreted in big H. So hence A inverse is an inverse, in fact the inverse, an inverse for A in the group, well, in H. Okay, so that's G3 proved. So as I say, you do have to keep in your head keep straight in your head what we're trying to prove here. But so you're going to use this result so many times, I did want to make sure we have a careful proof of that. You might want to reread the version in Fraley, which is pretty much the same as this. I've expanded it a bit. You might want to watch the video again of the proof here. So it is a result we're going to use a lot, so you should make sure that you've proved it once and for all. Okay, so perhaps I'll just write a final sentence. So we conclude that, having checked all the conditions for a group, that H is a group. And so it's a subgroup of G. Okay? So let's do a quick example of using this. And it's going to be pretty similar to the examples we did in the tutorial yesterday, but I don't think it does any harm to do another one. And it'll serve a purpose, this example, to introduce another important group to our list of groups. So let's take the general linear group. We take it over the reals, but you could replace the reals here by the rationals or the complexes or the integers if you wanted. So this could be the integers or the rationals or the complexes or the integers modulo 2, whatever you wanted. Some nice number system, to be technical, some ring. But let's choose the reals for definiteness. And n is some natural number. So this is the general linear group, or a general linear group. So this is the group of all invertible n by n matrices with real entries. Just to remind you, this is a really important group. It's a group of all square matrices which are invertible, got real entries, if that's the reals, under the binary operation of matrix multiplication. So the general linear group, the binary operation, is always matrix multiplication. So we can multiply two square invertible matrices together, we get another invertible matrix. We haven't actually proved that in class. It's something I hope you would have seen last year in linear algebra. We can, if you want me to prove that in tutorial, then just ask me to do so. But this is a group, the general linear group, or one of the general linear groups. We can change n, we can change r to another favourite number system. So we've got a whole collection of general linear groups. Well, we're going to look at a subset of this and then prove it's a subgroup. And the subset we're going to look at is actually quite an important one in its own right. So perhaps I'll put it on another sheet. So I've got some space. So we're going to look at a subset of GLNR. So it's going to be all the matrices in GLNR for which the determinant is 1. Okay, so some matrices in GLNR have determinant 1. And we put those all in a bag and we call that H. And the claim is that H is a subgroup of G. So remember, we use this symbol for subgroup, this less than or equal symbol for subgroup. So it's a pointy symbol as opposed to the rounded subset symbol. So we're going to use the subgroup test. The theorem that we've just proved. So we've got to establish that conditions 1, 2 and 3 hold. So this is a typical example of using the subgroup test. We're going to go through conditions 1, 2 and 3 and check that they all hold, and then we'll deduce that H is a subgroup. So condition 1. What's condition 1? That was closure under the binary operation on big G. So how do we check closure? We have to take two elements of H, we have to multiply them together, and we've got to check that we stay in H. So let A and B be in H. And I want to look at AB. So I'm writing this out in a fair amount of detail. As you get a bit more practice with these things, you could perhaps miss out one or two of the lines, but if in doubt, put the lines in, is my advice. So I'm going to consider AB. Well, AB, I can certainly multiply these two matrices together, and that's going to be an element of big G. What I want to do is to show that this is actually an element of big H. So certainly this product is in big G, in the big group, because we had a group there to start with a binary operation. I actually want to show that AB stays in H. How do I check that AB is in H? Well, I've got to look at the definition of H. And H is all the matrices for which the determinant is 1. So to check that AB is in H, I have to compute the determinant of AB. Of course, depending on what example you were doing, the details here are going to change a little bit, but the overall structure of this proof is the one that is a kind of template for how you're going to do it in general. So here I have to compute the determinant of AB, because H is defined in terms of the determinant. Well, I'm going to use this really, really important result about determinants. I mean, essentially that determinant is a homomorphism, but it's the determinant of AB is the determinant of A times the determinant of B. So that's one of the most crucial facts in mathematics, I would say, that the determinant has that property. Now, as always, there are some right-hand sides to write down, which I'm not writing down. Well, I have an excuse now that I've got no right-hand side on my sheet, but I hope you will be writing right-hand sides down in your own work. I always say the reason, so that follows because of a property of determinant, which we use all the time. Now, I'm going to use the fact that A and B are both in H. So the fact that A is in H means the determinant of A is 1, because that's how H was defined. So this is 1 times 1, because A and B are both in H. And 1 times 1 happily is 1. So we've got the determinant of AB is 1. But that says that AB qualifies to be in H. Okay, so we've now checked closure of H under the binary operation. If we multiply two things together, both of which live in H, we stay in H. Of course, it did hinge on the crucial property of 1 here, that 1 times 1 equals 1. And as we saw in one of the examples on the exercises that we discussed in at least one of the tutorials yesterday, this wouldn't work if we were looking at determinant equals 2, for instance. Okay, so that's closure under the binary operation. What about an identity element of G? So consider I. Well, let me just remind you what the identity element of the general linear group is. It's the matrix with 1s down the principal diagonal and 0s everywhere else. So big G, remember, is the general linear group. It has an identity element, which is the identity matrix. What I've got to do is show that big I is in big H. That's condition 2 being checked. Now, this is just to say something again, at the risk of boring you, that I said in the tutorials yesterday. When you are working with a group, for instance, here we're working in the general linear group, that's the arena in which we're working, you must make sure that you know the properties of that group. So you must make sure you know what the binary operation is, it's matrix multiplication. You must make sure that you know what the identity element is. And the identity element is this matrix. So let's check that this is also in big H. How do we check that it's in big H? We compute its determinant. And we're just using facts that we know about matrices. The determinant of this matrix is 1. So hence, big I is an element of big H. Sorry, my set membership symbol seems to be getting bigger and bigger, but hopefully it'll stop expanding before the end of the class. Okay, so big I is an element of big H. So that was condition 2 checked. Because remember, condition 2 says the identity element of the big group is in the subset that you're considering. And finally, condition 3